Hello friends, I am Satyendra and today in this video I will explain you what is the Ising model and how it explains the phase transition. Okay, so Ising model is the dynamical model of phase transition. Okay, so in this model we assume that our system is an array of lattice sites, okay, with only nearest neighbor interaction, okay, and this interaction depends on the manner of occupation of the neighboring sites. Okay, so if you don't understand this definition right now, don't worry about it, because later in this video I am going to explain you in more detail with the help of equations and example. Okay, so don't worry. Okay, now this simple model can explain ferromagnetism to antiferromagnetism transition, gas to liquid transition, liquid to gas transition, and many more. Okay, but for here we will consider only the magnetism. Okay, for our explanation purpose and to develop the theory we will use only ferromagnetism. Okay. So friends, now to study the statistical mechanics of the Ising model, we take some assumptions here. Okay, and the assumptions are as follows. We disregard the kinetic energy of atoms, okay, which sits at various lattice sites. Okay, and then the phase transition is essentially the result of interaction energy among atoms. Okay, so that is the fact, and we include only the nearest neighbor interaction. Okay, so in this model, to explain the phase transition, only the nearest neighbor interactions are counted. Okay, the third point is that to study the properties such as magnetic susceptibility, we subject the lattice to external magnetic field B. Okay, so there is a reason behind this. You need external magnetic field if you want to if you want to calculate the magnetic susceptibility. Okay, so let me explain you this in a little bit more detail. So you can see that here that the this susceptibility depends on the magnetization M. Okay, and this magnetization M further depends on the magnetic field B. Okay, you can see here. Okay, it is written very clearly. Okay, so that's why whenever we want to know the susceptibility, so we have to subject the lattice to the external magnetic field B. Okay, and don't worry, I will explain you in more detail about all these things. Okay, so now let's come to the fourth point. Since the atoms possess the spin, okay, whatever is sitting at the lattice sites, they possess some spin. Okay, so in the and also the lattice is subjected to external magnetic field B. So that's why the atoms possess the additional potential energy in the presence of magnetic field, and that potential energy is given by this expression here. Okay, so in this expression, mu is the atomic magnetic moment. Okay, and the atomic magnetic moment is given by this formula. Okay, and don't worry if you are unaware of this formula, because this formula has came from the quantum mechanics. Okay, so in this formula, G is the Linde G factor, mu B is the Bohr magneton, okay, and J is the total angular momentum that comes from the quantum mechanics. Okay, so don't worry much about this, because we don't need this in much detail in to develop our theory. Okay, so you can only keep in your mind about this fact. Okay, so now also in this formula, the other quantity is the B magnetic field, and the third important thing in this expression is the sigma I. Sigma I is the spin of the atoms that sit at the lattice site. Okay, so sigma I is the spin value assigned to each lattice site. Okay, this sigma I can be +1 or -1. Sigma I is +1 when the spin is up, and sigma I is minus when the spin is down. Okay, so it can be sigma I or sigma j, that does not matter. Okay, now okay friends, now here you can see that there is an external magnetic field as I have written. So this is the external magnetic field B, and you should never get confused with the B with the magnetic induction. The B here for our case is the magnetic field, and the unit of B is ampere per meter. Okay, and this magnetic field, what is the meaning of this magnetic field is what I am going to explain you. Okay, so sometimes magnetic field is also denoted by H. Okay, so the magnetic, what is magnetic field? So it is the capacity of the magnetizing field to magnetize the substance. Okay, so its unit is unit of magnetic field is ampere per meter. Okay, so you should not get confused magnetic field with the magnetic induction. Okay, so what we have used here is the magnetic field. Okay, okay, so now okay, let me also tell you what is the magnetic induction. So in a magnetic the magnetic induction is also has the notation B. Okay, it is also denoted by the magnetic B. Okay, so the unit of magnetic induction is quite different from the magnetic field, and it is Newton per ampere per meter. Okay, which is called Tesla in SI units, and it's also its unit is also given as Weber per meter square. Okay, so you can keep in your mind about this. Okay, now what is magnetic induction? So magnetic induction is a measure of the magnetic flux density within the substance. So basically the magnetic induction gives you the magnetic flux inside the substance. Okay, so it counts the number of magnetic lines that pass within the substance. Okay, okay, okay friends, so now let's develop our theory about the Ising model. So uh, to develop the theory, you need to consider a system. Okay, so we consider our system in this configuration. Okay, this in this configuration here, sigma I, sigma 2 are the spin assigned to the lattice sites. Okay, so you can to understand it better, you can consider here that this and this are the lattice sites, and each lattice sites have the spin. For the first lattice site the spin is sigma I, for the second lattice site sigma is sigma 2, and so on. For the last site the sigma spin is the sigma n. Okay, so in this configuration, if you want to write the Hamiltonian of the system, okay, so that Hamiltonian will become like this. So the Hamiltonian will be the functional of sigma I. Okay, so now, so this Hamiltonian is equals to this quantity plus this quantity. So okay, so what is this quantity, friends? So this quantity is the exchange interaction term. Okay, so this term basically comes from the interaction between the two nearest neighbor sites. So for this, here we only take the nearest neighbor interaction. Okay, so you can easily see that I have written it nn. This n dot n, that means that nearest neighbor. Okay, so sigma I and sigma j are the spin of nearest neighbor. So okay, so let me explain you in more detail. For here, let's consider here. Okay, so this is sigma 1, this is sigma 2, this is sigma 3, this is sigma 4. Let's consider only 4 things. Okay, so let's consider here the spin is up, here the spin is down, here is the spin is up, here the spin is up. Okay, so okay, so this is the, here I have written the spins. Okay, so when you write this expression, then that will mean that you will only have to consider the nearest interaction. Okay, so then this whole term will become like okay, minus j. So first we will take this two interaction, sigma 1 sigma 2, plus then we will take only this interaction, sigma 2 sigma 3, then we will take this interaction plus sigma 3 sigma 4. So okay, so only these much interactions are counted because we are only considering the nearest neighbor interaction. Okay, so since this is up direction, that means it is +1, this is -1. Because of down direction, this is +1, this is +1. So if you solve this thing, then what you will get? So let's see it. So okay, so sigma 1 into sigma 2, that will be -1, and then this will be plus, this will again be -1, and this will be +1. Okay, so finally your expression in this here, it will get cancelled here, and finally you will get plus j. Okay, so this is how you get your interaction energy term when you solve for the questions. Okay, now let's see what is this term. Okay, so in this term is nothing but this term comes because of the magnetic field, because we subject our lattice to the external magnetic field. That's why this term has came. So this term just is just the it's just the additional potential energy that has developed in the lattice due to the spin. Okay, so it is clearly written here, the term due to interaction of the spin, spin sigma I with the magnetic field. Okay, so let's explain you this in a little bit more detail. So if there are, I have already told you, if there are, let's consider if there are 4 spins. Okay, sigma 1, sigma 2, sigma 3, and sigma 4. Okay, then this term will just become like mu b sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Okay, then that means for the 4 spins, their total potential energy will be like this, and that will be added to your Hamiltonian to create your total Hamiltonian in the Ising model. So okay friends, so in the Ising, so this equation is called the Ising model. Okay, so you can always keep in your mind that whenever you are dealing with the Ising model, if there is no magnetic field, okay, if the lattice is not subjected to any magnetic field, then you can only retain this much part. Okay, you can only retain this much part, and if the lattice is has been subjected to magnetic field as well, then you have to keep both the terms in your Hamiltonian to solve the equations of the Ising model. Okay friends, so in this Hamiltonian, you have seen that there was a term J, and this J is the exchange energy. Okay, so exchange interaction occurs between the identical particles. Okay, and this effect is due to the wave function of the indistinguishable particle being subject to exchange symmetry, and this is the quantum mechanical effect. So friends, this exchange energy develops because the indistinguishable particle, when get exchanged, they have the exchange symmetry, and you cannot say that whether they have exchanged or they didn't exchange. So that basically this effect basically comes due to the wave function of the indistinguishable particles. So you don't have to go in much detail about this thing. Okay, so for the time being, you can only keep in your mind about these things, and let's proceed further. Okay, so now there are some authors who write this equation in different ways. Okay, so let's consider about different ways of writing this equation. Okay, so let's come first to this equation, this way of writing. So in this way, your sigma I is just replaced by Si. Okay, so your spins are now denoted by Si, Sj. Okay, and it is exactly similar to this expression. Okay, it is exactly similar to this, and this is your additional potential energy, which is also similar to this. Okay, so here also the sigma I has been replaced by S subscripts I. Okay, and this whole Hamiltonian has been written for n atoms. Okay, so that's why here you can see that there is a summation I equals to 1 from 1 up to n. Okay, and now here you can see that we have written the n dot n, that means nearest neighbor, and here that has been replaced by ij. Okay, so that this also means that the summation has to be done only for the nearest neighbor interaction. Okay, now thus Si is equals to +1 for the up spin, and it is equals to Si is equals to -1 for the down spin. Okay, and this summation is the sum over nearest neighbor spins, okay, that I have already explained you. Now let's come to the different ways of writing this term. So since different writers write it in different ways, so students get usually confused with this. That's why I have written all different ways of writing this summation in here at one place. So here you can see that this nearest neighbor interaction can be written like this, means summation over nearest neighbor can be written like this, okay. And and that thing can also be written like this, in this way, and that sum over nearest neighbor pair can also be written like this. So there are different ways of writing the same thing, okay. So students should never get confused with this thing, okay. So now friends, after having too much discussion about the Hamiltonian of the Ising model, this is the Hamiltonian of the Ising model, let's consider about the partition function. So the partition function in the Ising model is written in this way, and I advise students to remember this partition function in the way of writing this partition function, because this partition function is frequently required to solve the questions in in statistical mechanics, okay, that the questions which are based on Ising model, okay. So now in this partition function basically depends on the magnetic field B and the temperature T, okay. And this partition function has been written for the n Ising spins, okay. So you can see that the way of writing this way, and you can also, if you want, you can by heart this basic equation, okay. So here what you see is the Hamiltonian of the Ising model, which we have already explained you here, okay. And beta is nothing but beta is just the is just equals to 1 over kt, okay. That is called the beta parameter in thermodynamics, okay. So now why we need this partition function, why it is so much important, friends. So the partition function is so much important because after calculating the partition function you can calculate the lots of properties of the system. So let's see what properties you can calculate. So you can calculate the free energy of the system. So Helmholtz free energy can be calculated using this formula, and you can see that in order to calculate the free energy you need the partition function here, okay. Here is the partition function that you will require to calculate the free energy. That's why partition function is calculated at the first time, okay. Means for the firstly we calculate the partition function. Now in order to find the internal energy of your system, you can use this formula, and in this formula you again require the partition function here, okay. You can see that we have taken the log of the partition function, and this partition function comes from here, this basic equation, okay. Now if you were asked to calculate the specific heat, then you have to use this formula, dou u over dou t, means T here is the temperature, and in order to calculate this specific heat you have to calculate the internal energy, and this internal energy will further depends on the partition function, okay. So to calculate the specific heat you will require the partition function. Now if you want to calculate the net magnetization, okay, then you have to use this formula. In this formula we are using the free energy, and this free energy further comes from this formula, which further depends on the partition function. So you will again need this basic equation to calculate your free energy, and then you have to calculate the net magnetization, okay. So now friends, you have to understand at this point that what is magnetization. So the magnetization is denoted by the symbol M, and it is also called intensity of magnetization. So the magnetization means that magnetic moment that develop per unit volume. So in the unit volume the number of magnetic moments that develop is called magnetization, and the unit of magnetization M is ampere per meter, and you can keep in your mind about this definition, okay. So now here the magnetic moments per unit volume is called magnetization. Then what is magnetic moment? The magnetic moment is given by this expression m into 2l. Here m is the pole strength and 2l is the distance between two poles, okay. So the magnetic dipole moment is given by this formula, and the number of magnetic dipole moments per unit volume is called the magnetization m, okay. Now friends, let's see how the Ising model explains the phase transition. Okay, so here we will see how it changes from ferromagnetic to paramagnetic. Okay, so let's see it. Okay, if the temperature T of our system, if the temperature T of our system, just 1 minute, is less than the critical temperature Tc, and the magnetic field that is being applied to the lattice is zero, that means in the absence of external magnetic field. Okay, in the absence of external magnetic field, if you calculate your magnetization from this expression, okay, using your free energy, and that free energy were calculated using this partition function that comes from this Ising model. Okay, so this magnetization, if you calculate, okay, for T less than the critical temperature in the absence of magnetic field, and when you calculate that magnetization and you find that it is non-zero, then this gives you the spontaneous magnetization of the system. Okay, and that gives you the spontaneous magnetization of the system. That means that m magnetization, which means the magnetic dipole moments per unit volume. That means if it is not non-zero, okay, that means if the value is not equals to zero, that means there are magnetic dipoles per unit volume, and that gives the spontaneous magnetization. Okay, so that means if the temperature is less than the critical temperature, and there is no external magnetic field, and then even then there is some magnetization is there in the substance, that means the substance is the ferromagnetic substance. Okay, and for if you increase the if your temperature is greater than the critical temperature, okay, then that simply will change to the paramagnetic behavior. Okay, and there won't be any spontaneous magnetization. Okay friends. So friends, now let's consider a important property, that is the magnetic susceptibility, that will explain you better how the phase transition actually occurs. Okay, so the magnetic susceptibility will depend on the magnetic field B and the temperature T, and that is equals to the first partial derivative of the magnetization M with respect to the magnetic field B. Okay, so this is the we always require the magnetic field whenever we talk about the susceptibility. Okay, so what is susceptibility actually means? So susceptibility is the measure of the extent up to which the material can be magnetized in relation to the applied magnetic field. That means when you apply the magnetic field H, okay, the unit of magnetic field is ampere per meter here. Okay, so when you apply the magnetic field H, then susceptibility means that up to how much extent the material can be magnetized. Okay, so that means that this is what the susceptibility actually means. Okay, so now as you already know that M is the magnetization, which is the magnetic dipole moments per unit volume, and H is the external magnetic field. So let's write this expression in the simple form here, so don't get confused here. In the above discussion we have used the symbol B for H. Okay, so here B and H are the same thing, both are the magnetic field. Okay, so now here, okay, so you can here see that x if the susceptibility is positive and small, the material is paramagnetic substance. Okay, and if the susceptibility is negative, then the material is dimagnetic. Okay, and if the susceptibility is positive and large, the material is ferromagnetic. Okay, so that means the susceptibility describes you whether the substance is paramagnetic or dimagnetic or ferromagnetic. Okay, so you can see that susceptibility gives you about the knowledge about the phase transition. Okay, so this susceptibility is calculated using magnetization, and this magnetization M is calculated using the free energy. This magnetization M is calculated using the free energy F. This free energy F is calculated using the partition function. This partition function is calculated using the Hamiltonian H. This Hamiltonian comes from the Ising model. Okay, so that means that the phase transition, this phase transition, paramagnetic, diamagnetic, ferromagnetic, this phase transition is explained with the help of Ising model. Okay, that's complete our lecture. Okay, thank you friends, thanks for watching this video. I hope everybody have enjoyed my video. So please support this channel, and subscribe, share and like this video. Okay, thank you friends. Okay.